DC biasing of bipolar junction transistors, part 4. Self-bias or emitter-bias calculations. We discussed this emitter-bias circuit earlier in part 3, and in this video I just want to discuss how we do some, or a couple of formulas that you will need when you do calculations on this type of circuit. So I'm going to begin by splitting the circuit in half like this. And first of all, considering the left hand side of the circuit and applying Thevenin's theorem. Now, Thevenin's theorem says if we've got a in order for us to work out the for us to determine the current that's going to flow into the base of the transistor, we need to consider this part of the circuit, which is the part that provides the current. And we first of all want to look at the open circuit voltage across the terminals at this point, the open circuit voltage across R2, and we can see that from as a potential divider, the open circuit voltage across this resistor is R2 over R1 plus R2 times the supplied voltage, which is denoted as VCC. The other thing we need when applying Thevenin's theorem is we need to sort of look back into the terminals and determine the input resistance or the output resistance, and effectively these two resistors sit in parallel to each other via the battery, so the combined resistance of these two is R, and where R is R1 times R2 over R1 plus R2, the simple parallel resistance formula. So we've now got an equivalent circuit for the biasing resistors R1 and R2 for providing the input current, and that is the way we want to now consider the base side of this circuit, as though it's composed of a supply voltage of V and with an internal resistance of value R. Right, now I'll just move these out of the way and provide us with put the symbols V and R into our circuit in order to proceed with the next part of the calculation, which is to calculate or to provide us with an equation for determining the base current. So we're going to consider this part of the circuit where we've essentially got a power supply V in series with the resistor R applied across the base emitter of the transistor, and the emitter is now in series with the resistor RE, forming a circuit. So I'm now going to apply Kirchoff's law to this circuit, and we end up with V equals IB times R plus VBE, the voltage across the base emitter resistor of the transistor, plus IB plus IC times RE. Okay, so that gives us the equation which we can use to determine the base current, given the resistors R1, R2, and plugging in a value for VBE, for maybe 0.65 or whatever approximation we use for that. Okay, and that will enable us to determine our base current. So we'll come back to this equation later. We're now going to ignore this left hand side of the circuit, and we're going to look at the right hand side of the circuit, and you can see that applying Kirchoff's law to this side of the circuit, we end up with VCC is IC times RC plus the voltage between the collector and emitter plus the voltage dropped across the resistor RE, which is IB plus IC times RE. Okay, so that gives us our second equation, which will be useful to us later. So to sum up this this video clip, this short video clip, we have got two equations which we need to be able to use for the base side of the circuit and for the collector side of the circuit, and you can see they are quite complicated, but if you can fall back on basic principles rather than try to memorize these formulas, I think you'll find that's the best thing to do. But very often you're given certain values, like the resistor values, and you need to calculate the base currents or collector currents. And so when you actually start to plug in some numbers or realise what you don't know and you do know, you can then juggle these two equations around to get what you want in your calculations. So hopefully I'm going to be producing a part 4 to this series where I'll do some calculations on with some real numbers on these using this form of biasing. So I hope this has helped.